Very good afternoon, all of you. We should wait for a few minutes to start this session. In between, I request Dr. Avinash, are you able to listen me? Means my audio is audible to you?
I can hear you nice and clear.
Yeah. So can you please just check if your slides are shareable to us?
Yes, let me try. You see my slide?
Yeah, perfect. It is perfectly fine. So I suppose we should wait for a few more minutes and we'll start the session in a couple of minutes, okay?
Sounds good.
Thank you. Thank you. Yeah. So I think we should start it now. So I welcome you all. Hello, everybody. And today we are at the day 4 of our series. And I found this is quite interesting for all of us, and it is a great learning period for all of us. And we are honored to have today Dr. Avinash Singh, and few words about him that he's a senior lecturer, associate professor at the School of Computer Science and the Australian AI Institute, Working Technology, University of Technology, Sydney, UTS, Australia, and the founder of the India Future Society, a think tank. He is also the co-chair of the IEEE Neuroaddictives Framework for Workplace, sponsored by IEEE Brain, and a member of the IEEE Standard Committee on the Unifying Brain-Computer Interface. Additionally, he is a member of Transhumanism Australia and actively advocates for promoting transhumanism. In 2021, he was awarded the Google TensorFlow Faculty Award to support and promote his work in BCI, followed by Australian New I Award in 2022 for innovation. He has also been featured in prestigious Rolling Stone magazines, ABC Radio, and Bloomberg. Working at the intersection of machine learning, cognitive neuroscience, and mixed reality, Dr. Singh is dedicated to designing and developing real-world neuroadaptive BCI systems. His current research interests include integrating AI technologies with cognitive neuroscience knowledge to explore cognitive functions, discover relationship between brain dynamics, evaluate everyday interactions, and make decisions to develop robust next generation neuroadaptive BCIs. I know this is a odd time for Dr. Avinash being a different time zone, and he took out this time and he was ready to share his knowledge with us. He accepted our invitation, so I am really overwhelmed with his response, and I really welcome you, Dr. Avinash, for providing your time and support in this uh, time slot. And we are definitely looking forward to hear from you and learn many things from you. So all is yours. The stage is yours, sir. So can you please proceed further now?
Thank you, Dr. Priyanka. Really first of all, honored to be invited by you. I'm always looking forward to share more knowledge. I'm from India as well, obviously. Now in Australia, so I'm very much interested that more BCI and similar progress happen there. So wherever I can even contribute a bit, I'm there if I can. So thank you for a nice introduction again. And good afternoon, everyone, I assume. If you are watching online and from very different zones, so good afternoon, good morning, or good evening, whichever works best for me. I'm here. It's not too bad. It's 7:30 p.m. here. So it's not too bad. So it's all good. Um, like Dr. Priyanka mentioned, so I work at University of Technology, Sydney as a senior lecturer, which is, we don't have associate professor and professor title, except the full professor title. It is like associate professor. And my title of talk, which is my favorite topic, and I think I'm working a lot. This term neuroadaptive itself is not from me. I took it from one of the professor from Germany, but I really like this idea itself, and I'm working on this field from about 8 to 10 years now. And I'm just keep trying to keep pushing in that direction to create more neural interfaces. Neural interface is a very similar term as brain-computer interface, so they are pretty much similar thing. And like Dr. Priyanka mentioned, so I'm in from computer science. So my background is computer science, but I also trained in neuroscience. So I got this nice combination of knowledge, which kind of give me a bit additional edge to put more applied nature of work. And that's where the neuroadaptive comes in. So on that, let's move on and feel free to message on the chat, I assume. And of course, by the end of the talk, if you want to interrupt, that's also fine. I'm happy to answer a question. So the work I have done so far is quite a mix in quite different field. Like I mentioned, applied is a big part of my work. When I say applied, essentially from certain definition, you can also call it translational neuroscience. That's where I do a lot. So I do all fundamental neuroscience studies and then use that knowledge to translate into an application. So these are some example of some of my past work. I applied this knowledge in controlling robot, even using gaming as a medium to understand something more, brain dynamics. Spatial navigation is one of the very important area because it relate to lots of cognition related issues when people get old. Mixed reality, of course. Why mixed reality? Because it just gives me a lot of more control to design my environment in a way that I want to perform an experiment. And like very similar to mixed reality, robot come in and out so many times in different result. And that's where human agent teaming, where agent stand for robot, is another very important area. So I have some video snipped in the later in the slide to show you what I mean. And this all work fall into neuroadaptation essentially. So my goal behind all this work, how to make some sort of symbiosis between human and the machine. Now, machine could be a robot, virtual reality environment, or computer device, doesn't matter, as long as this could be some sort of relation. And I think, I mean, there's so many definition of BCI or neural interfaces, but what I do, I think they all apply to either replace, restore, or enhance cognition in certain way. And this is all happen, this all work I'm going to show you is a combination of last 6 to 8 years. So maybe not too much detail, but give you an idea what kind of work I do, and happy to follow up later on as well if someone interested in. So in addition to that, I should highlight beyond traditional neural interfaces or beyond brain computer interfaces, it's not just me, pretty much all BCI researchers around the world going a bit beyond in the field. And you might heard speech reconstruction, where just using thought to speech, and similar to thought to image reconstruction, which is I'm also doing here in UTS, or even the persuasive text, which is all about how to put the text. It's a little bit like a speech to text. So that's also another direction. I think pretty much whole BCI world is going forward, going beyond those traditional BCI we have seen in the past. Everyone know this is how BCI work, right? You get the brain signal. So by the way, I do non-invasive BCI. So nothing required. I open the scalp and put the electrode. No, I don't do that. And also my lab doesn't allowed me to do that either if I even want. So we do all EEG, which is a very non-invasive sensor, and I believe so many of you who's attending now familiar with EEG. And obvious step, pre-process and extract the feature of specific thing. So this all fall under very much neuroscience, cognitive neuroscience. And once I have enough knowledge what I want, given a specific stimuli, I present it to user or participant. Of course, I have the ability to, develop machine learning algorithm, translate into whatever metrics I want, and that metrics feed into these interfaces. Like I said, it could be robot, computer, virtual reality, mixed reality environment, and so on. And not to mention, these interface basically again feed into the user because user is looking at them, and it just go in the sort of closed loop manner. So that's this first three step is all neuroscience, cognitive neuroscience, and remaining part is a mix of artificial intelligence, human computer interface, and designing, and so on. And that's according to me is a translational neuroscience, and that's what I do essentially. Now, the talk is all about neuroadaptive BCI, and this figure I took from a book from Stephen et al. 2021. If you search this book, this is the term logic come from him, professor in Germany. And you can see in this picture, what you're seeing here, a user sitting on this Boston Dynamics dog. So, and wearing a headset, which is essentially a mixed reality headset. And his brain signal is feeding into some robotic arm and so on. So it looks a little scary, I can see that, but essentially neuroadaptive BCI this is an indication, interface that let you adapt just by your brain signals, all surrounding in a way that essentially align with what you are required. So it could be a mix of several biomarker, but of course I'm going to talk about one specific one which I'm very interested in. And among those biomarker, which is, like I said, there could be several. So it could be mental state related biomarker, like stress, mental workload, fatigue, and so on. Or it could be even more specific biomarker, which I work on in the past, and I'm going to show in the following slide. But one additional thing I want to highlight here is um, why neuroadaptive BCI? Why not other kind of BCI? So neuroadaptive BCI essentially fall under a category of brain-computer interface or neural interfaces, which is a passive in nature. And when something is passive in nature, compared to very active interaction in BCI, there's a more chances to tolerate the errors. So even something wrong happen, so motor imagery, for instance, is a very common neural interfaces. It has been used with lots of different research in the past, and it still is quite in use, but require a lot of training and so and so on. So lots of difficulty there. But in addition to those difficulty, it's also chances of motor imagery get wrong is also still very high. But when we talk about passive BCI, like neuroadaptive BCI, you actively doesn't really control anything. Your brain signals simply feed into whatever computer or system you're using, and that system, with the help of your algorithm or machine learning model or AI inside that model, use that information to adapt the surrounding. And that's the best part I like. And I think this kind of open up so much different application which can be think of, from medical purpose to entertainment. And that's the goal here, maybe also what I involve in. So this all started interestingly with one of my experiment I did quite early. I actually in 2016, where essentially I was trying to understand what happened when you interact with an object in virtual reality environment. So I'm going to show you a video. So this is a headset you see here, it's called HTC Vive, one of the earlier version, and the user is wearing 64 channel EEG cap. So there's a 64 sensor that can acquire the brain signal simultaneously. And there's some other equipment is in there called leap motion that kind of track the user hand in this environment. And then we ask user to, so user can see his real hand in virtual reality environment. So it's like you can see in the screen, there's a white looking hand. Actually, it's a user hand. It's a very much in real time. So when user really move the hand back and forth, user see the same thing in virtual world. And then you see this little red looking thing is in that, this is table, and the table there's a cube, which is a red and white. And we just ask user to perform this task. It's this task known as object selection task, very popular in HCI field. And we just want to understand how BCI can help here, or if BCI can be used to evaluate how good user is interacting with this cube or not in virtual environment. Because then we can create some sort of metrics and so on. That's the idea originally. And when we doing this experiment, what we did, so when we hold a cup of in our hand or a glass in our hand, every time when we try to hold, we know when we already gripped enough that we can start moving the cup around. And this is we learn over, childhood to wherever we come from, and that's how we know how to hold something. But when you're on the virtual world, maybe there's no haptic feedback. You don't know you're touching something or not. So you heavily rely on the eyes. And when you just rely on the eyes, so there could be so many things which could go wrong and change your experience. And that's what we're trying to understand here, how to improve the experience of user when they're interacting in the virtual reality environment. That was our original idea. And when we did this experiment, it looked like this, for example. Let me play this video. Oops. Because I'm sharing my screen, video might not be very good quality. I hope the live version of YouTube showing it very nicely. So you see user is touching this cube with their dominant hand. Cube is changing the color as a feedback showing user, okay, you touch it nicely, no problem. So this is again in the slow motion just to show you what's happening here. We have to give a feedback because user doesn't have a haptic as a feedback here. And when we change this feedback indifferently, so you see in the following few seconds, when user touch the cube, which we call conflict condition, user the cube already changed bit early, like a very little early, like half a second early. And when we did that, user is like, what is going on here? And although user have this visual input as a feedback, user brain is picking up certain signal, and those signal what we call conflicting signal. So this is not obvious behavior of something like a cube. And that's where we find, okay, this is interesting to, wow. Uh, Let me go next. We found that there is something called cognitive conflict occur every time user interacting in such a scenario. And we found using EEG that this all happening specifically in the part of the frontal area of the brain, more specifically anterior cingulate cortex, which is essentially known as a conflicting monitoring center. Very fascinating area of the part of the brain. Essentially, it controls literally everything else in the brain. This is where the command issues. So what this part of the brain indicating every time those conflicting happening in virtual reality is just showing me some changes in theta power, which is an indication that, okay, something is not obvious. There's a bit of mismatch. What I know in the past, what user know how to hold a cube is not the same as what the user is, experiencing when the conflicting situation occurs. And this conflict monitoring center, which is the frontal part of the brain, showing me those signals, those sort of biomarker, measure in the combination of something called event-related potential as well as in theta power, we call it event-related spectral retribution as well. And we use that signal to essentially predict very nicely how much user is feeling this conflicting situation. We also able to predict how I can use this information to change something. So if I go back and define it, essentially what happening, we were able to measure every time if there's a discrepancy between expectation and reality. Reality is what user is experiencing now and what he is supposed to expect. Now, expectation is all come from the user's experience. So what user has experienced before. And this also happen essentially, literally every single step we do. For instance, uh, when you start learning a bicycle, very first time, because you don't know how to pedal it, there's a bit of experience, and that's where the cognitive conflict monitoring already start happening. And over time, you get to learn more and more, and you adapt. So that's how brain literally do all the things. So whenever learning happening, maybe there's a cognitive conflict is also happening. But that also means cognitive conflict might cause some other mental state. For example, if I ask you to keep learning, keep having conflicting situation, you might start feeling more mental fatigue. You might start feeling more mental workloaded because you can constantly, using processing a lot of information which you have never seen before. Maybe it's exciting as well, but most of the time it just make you more fatigued. So we thought, why not? What we do, we use this information, feed into the system surrounding to the user in a way that user experience such a conflict become less. So what that mean, we want to feed the information in a way that if user did something wrong, which is not same as expectation, we make this actual experience of the user. And by doing so, we apply this information in so many different settings, like I just mentioned before. We did this with the robotics, where human and robot is interacting with each other. When I say interacting, they're actually working together. So user is holding the robot, and robot is a semi-autonomous in nature. We did this to understand if user have confirmation bias, which is a very interesting study we came across. This is a soon to be published work. This is not too far away we did. So actually, you can also predict by their cognitive conflict monitoring if someone is more biased or not biased, interestingly. This is one way. So user is just looking at some facts and opinion, but then we translated those bias statement between two people when they're talking with each other. Again, we were able to measure this information, which is very interesting. Of course, there's a bit slightly change in biomarker. We also have to adapt the algorithm in that way. But fundamental concept or anterior cingulate cortex or frontal part of the brain stays same. And the continuous of the experiment I did with the virtual reality, We also extended this by providing a haptic feedback. We design some sort of a sensor and you just synchronize it, a bit of engineering work there and just still try to predict. So you can see this is a nice ERP diagram showing, if it's not so clear, but yellow is essentially um, EMS, vibration plus visual, essentially all so much feedback user receiving, more feedback user receiving, and more cognitive conflict actually is happening. So that's another interesting finding we found, which is more rely on virtual reality, but also means more sensors you feed to the user, your cognitive part of the brain, which is a conflicting monitoring center, experience even more stronger prediction error. So that's another fascinating thing. And like I say, I'm applying this here and there. So that's where the whole neuroadaptive thing also actually started. And this is quite fascinating itself. So these all are published work, except a couple of them and soon to be coming up. So like I said, oh, right, something missing here. Um, never mind. So essentially, what I'm trying to say, neuroadaptive essentially is nothing more but a closed loop feedback system where brain signal use to detect cognitive conflict, and we use that information to adapt different things. Now, different things could be so many possible things. One example which I really like is, think about you're reading a Kindle book, and every time you read, going to next chapter in the Kindle or next page in the Kindle, which is a digital book essentially, we just adapt what content should be there just based on your brain signal. And that's a kind of hopefully the future you're gonna see as well. And that's why I'm saying after artificial intelligence, I think BCI is another big frontier ahead, which is gonna change everything, how we interact. Oh, okay, I can
Dr.
see more.
Avinash, I have a very basic doubt. What we are talking about, is this the combination of BCI as neurofeedback also? Means when you are talking about the giving and take kind of stuff, so means two-way round. We are processing the information of brain signals as well as we are providing the feedback to brain processing. So is this kind of a neurofeedback system associated with BCI?
I
No.
would not call it neurofeedback because user is not adapting. We are not relying that if user adapt or not. Neurofeedback is where user actually somehow know how to control things.
Yes, yes.
It's more of a taking signal and feeding into the system. So it's also possible over time those, because user is actually constantly taking those signal all the time, obviously, and algorithm has to adapt that biomarker changes over time, which is a constant problem of BCI all the time. So it's not neurofeedback. I would not call it neurofeedback, but I can understand why it might feel like a neurofeedback. But here is a neurofeedback is more on human brain. We are doing adaptation on the system outside the world, not the
Okay.
human.
Got it.
And
Got it.
that's a major difference between this one and that. And like I say, think of another scenario, which is I find maybe we're gonna see, we are trying to do an experiment on that, where think about you know how to drive a car, and after several years of experience, I gave you a new car or you bought a new car. What happened? You bought new car, maybe steering of the new car is a little bit more stiff. The brake is very sharp, very strong that you just push the brake and just accelerator might be different. And again, as a user, we just learn maybe a few days of driving and we adapt to the new car. Having neuroadaptive system, maybe your car learn from you and know what you need, and car become more, what we call it, compliant essentially based on your need. So essentially, instead of 3 days of learning period, maybe in couple of hours, and car is already behaving like your old car. So there's a good and bad
Actually,
advantage.
that's a very important means that's a very clear example you have given. This very interesting actually. Yeah.
So like I say, it's a good and bad thing. Good because maybe then you just pay attention to more important thing first, which is maybe every the world is moving toward more quick turnaround time. But at the same time, could be limitation or disadvantage could be it might make you less adaptive over time. I don't know. That could be some another study itself, longitudinal, to see how it look like. So let's see some of the example I did in the past with respect to this kind of work. So like I said, one of the very first one is called human agent teaming. Now, agent is essentially a robot, and human is, of course, human. And teaming because they are working together. Now, when I say working together is when two people working together, especially we call two people who are working together, who are very nicely as a teamwork, but sometimes we also know people who are not working together is not so good to go with each other, constraint and requirement. So we created a system. Like I said, based on cognitive conflict, that's a fundamental biomarker. Use some reinforcement learning. And we talk about a robot which is a physical human robot, right? So what's the difference between a standard robot and physical human robot? In the physical human robot is a semi-autonomous kind of a robot, but the same time, you have to kind of direct the robot in a direction you want it to perform a task. So that kind of robot is called a human, physical human robot or PHRC. So we created a framework, I call it NEUROADAPTIVE framework for PHRC, physical human robot collaboration, using algorithm that constantly adapt. It's very similar to what example I gave about the car. So what this system does, even you have never used such a robot. Robots somehow become compliant over time, which required a lot of training in a standard setting in very short time. So essentially just accelerate the training curve, which required just because of neuroadaptive feedback or neuroadaptation in the robot because of the brain signal. By the way, robot look like this. If you see this figure where user is wearing a suit, the robot, we actually are going to show you the picture. This is the robot. This is the video where this user is playing a game. Of course, well, this robot is called blasting robot. When I say blast, not a bomb blast sort of blast, but blasting as it just blasts the sand from the nozzle of the robot and it just scrap certain things from the wall. So it's like a cleaning kind of robot. That's the purpose. It's an industrial robot. That means the nozzle has so much power to throw the sand on the wall. And if you just have to hold nozzle, the pushback from the nozzle is so high. So robot is somehow manage that control. So when user is using and holding this robot, user doesn't even feel that power because robots somehow take care. And that's where this physical human robot collaboration comes in. That's where they're collaborating. So what user has to do, simply hold the handle and move it around where whichever direction user want it to. But sometimes robot doesn't move in the direction if there's a safety issue or because like I say, it's a very powerful robot. It's very easily can cause an accident. So we thought, can we try EEG to feed this information in the robot? Of course, instead of doing a blasting, we design a simple game to perform an experiment, which you can see here. Again, let me try. Very simple game where user have to simply move the nozzle from left to right, right to left, following the instruction indication of those yellow and green and red dot. And sometime we give user a conflicting situation and just see how algorithm can adapt. It's little bit difficult to see in this little demo, but what essentially happened, user want to move it left, even in the strange angle, still robot know how to go straight and more smoother version of it. So robot somehow learn over time as user keep interacting. And the best part of this work I like because I use the reinforcement learning here, which is very popular to provide the learning curve between human and the machine. But I haven't seen any work out there where this happen in the real time because generally reinforcement learning kind of a machine learning algorithm required millions of trials to adapt. Now think about user is doing millions of time, this thing is impossible. So we shortened this in 30 minutes to 1 hour, and still it worked pretty nicely to prove this concept. This is another published work you can see. I think it's still in archive, and it's called, like I say, it's called NEUROADAPTIVE Framework for Physical Human Robot. Another work, which is a continuous form of this work, like I say, I wanna see adaptation. Just happened to done by a student recently, but I thought to put this video here. This is called gripper, another robot, and we are feeding the brain signal here into the gripper. So gripper is like a hand or prosthetic, for instance, for the user, and gripper learn how much grip gripper should have to hold something. Sometimes it could be over grip, sometimes it's an under grip. So this is like a under grip example where user is far away to holding an object. And this is the example of previous videos, example of over gripping, where you just hold something very tight. Now, this algorithm, which I just showed, neuroadaptive, this can do what it can do, it just know what's the best way to hold something. Just looking at the eye, we don't need any other signal, and the brain signal, obviously. And it's a very classic problem in prosthetic to give the feeling of user. For some reason, we know very well how to hold an egg and a tomato and a stone. We know how much grip to put in there so they don't break or something happen. A robot is not so great in that. And so that's another example of similar work. We thought, okay, we can do neuroadaptation now, but what if user is already in so much stress or maybe mental workload is there because of the difficulty of the task? And interestingly, what we found with neuroadaptation or cognitive conflict, what I call it, they are so much related to each other. So user doesn't respond well with cognitive conflict if user brain is already overloaded. So we did one study with cognitive load of for neuroadaptation. So the example I'm showing is mostly focused on cognitive load, which is a mental workload when you are so much in the task that you can't bear any additional input from the surrounding. And we did this task with ATC. So ATC stands for Air Traffic Controller. And when I say air traffic controller, their task is actually one of the most mentally demanding tasks. Why is that? Because although they have a computer screen on the dashboard, if you see a tower in the airport, that's where the ATC people stand. And they just simply keep monitoring the how many which plane is landing, which one is taking off, and so on. And because this work required a lot of effort to avoid any mistake, because any single mistake could be very fatal for a passenger, so they don't really necessarily need to work every day. So they get a lot of break so that they can recover from that module. And we did this work with the ATC to try to find, is there any way we can design a system? First, we of course study some similar setting and design a system that not just know when user is cognitive loaded, but use the machine learning to provide them some sort of assistant, because that's when the user or this person, which is ATC controller, doesn't maybe not able to perform the task as the good as possible. So we designed this task, and I would recommend you try to follow it. So think of this dot as an airplane flying, and you have to track a specific one. Let me go back. So you see this blue dot, and after a second, this blue will change to red, and you just have to keep eye on that. That's sort of the thing what ATC does. So let me play it again. Oops. Oops. Right. And on the right side, this is a real-time monitoring system. Essentially, we call it a meter, just for demonstration purpose, showing the cognitive load is going high. So when you follow one dot, That's not too bad. It's okay. But when you start following 3 dot, things start becoming a little bit more complicated. This is a classic task actually to measure cognitive load, but here we're representing this is very similar to ATC task. So user still can respond and all 3 are correct. Now this one is a complicated one. So you find now you have to follow almost 5 dots. It's very easy to forget which dot is where, and that's where the AI kind of taking over and just provide an assistant to user. And that's the goal of this particular work. And again, NeuroAdaptive came in existence because we adapting this nature of the task to the dashboard on the screen. And like I say, I just keep applying this in different setting and also thought, why not we try this in the NeuroAdaptive training, which is another task where user is using mixed reality headset. And what we did with the user participant, so user and participant, the same thing here. Well, it's very difficult to control the video. I'm trying to play it. Okay. So this is user, which is a captain and trying to drive the ship in the water as fast as possible. Now, at some point, what we did, user can read lots of information, which is from the dashboard on the right side of the ship. So it looked like this. So you see the dashboard on the right side, there's a big computer screen, there's a map and so on. A user just have to take the readings from there and just navigate. So navigating a ship is very different from driving a car or scooter. It doesn't stop the same way, it doesn't navigate the same way. There's a momentum and so on. Whenever we think user cannot handle it, we provided them this kind of information. So this is like a head focus interface, or it's called head up interface. So now user, instead of going on those computer screen, user can just look at these information on front of screen all the time. But the problem of such an interface, the user is also information is too much overloaded. It's all the time is there. And it's not very good to make decision if user has to do. So we also simplify it further based on the feature and we make it look like this. Now the same interface, the map is disappear. We just see some yellow icon, which is representation of the ship around the ship, which the user is on, and user just have to complete the task. So this is the adaptation we did. So essentially, how much information to present to the user if you are in such a setting, that was a goal of such a task. And again, neuro adaptation was pretty good to do that. So if I show you what it looked like, we did these 3 different kind of setting. Like I say, one is very classical dashboard thing, which you can see in very beginning of the video, or they can see some map and the icon and radar kind of thing always in front of the user, or even further reduced version of it. Well, the goal of this study, obviously, you want to understand if augmented reality kind of interface is really helpful for the user or not. And we find, yes, it's helpful, but too much information is not helpful. And we have to find a mechanism to adapt here. And interestingly, we haven't even used EEG here. We simply use the eye tracking data to do everything. Because again, although I'm saying neuroadaptation, but it not necessarily has to stick with the brain data. It might also reflected in some other physiological data like eye tracking or heart rate and so on.
Yeah, Dr. Avinash, shall I interrupt in between to ask one question?
Yes,
Yeah,
yes,
my
please.
concern is that means how what is the actual basic method by which you are calculating that cognitive load or cognitive conflicts? So means neurological aspect I wanted to understand whether it is via EEG, via some particular lobe, via some particular brain waves or some range or PCD or alpha symmetry. If you can let us know about bit more that would be very helpful.
So most of this work is all based on EEG. And like I mentioned in very beginning, so theta is the key element here, theta power. So theta power modulate whenever you are facing cognitive conflict. And I haven't mentioned too much detail, that's right. So so you can see this modulation within the 2 to 300 millisecond. It's very much like a mismatch negativity concept if you search somewhere about EEG. So within 2 to 300 millisecond, after that mismatch or cognitive conflict happen, you can detect that in the brain signal. So it's pretty fast
So this is again
compared to
would be a ERP.
you can
Okay,
use ERP, you can use the power like a frequency domain, or you can use a combination of both too. That's
fine,
okay. So
fine.
if you look at the frequency domain, there's a theta. If you want to look at the ERP alone, then that's where the 200 millisecond is a very clear negativity peak in the signal that's a reflection of this information. And like I said, so except this work, which I'm showing in the screen at this moment, we haven't used EEG at all. We simply try to use eye tracking data, pupil dilation, and so on, just because of complexity of the experiment and
Got it.
because we talk about ship navigation. But all the previous work is all using EEG and theta power. But again, to be honest, when we design the machine learning algorithm that can continuously predict the level of cognitive conflict based on those features, maybe machine learning even bit more than I know. Maybe not just 200 millisecond, maybe there's something else. So actually there's another feature which is around 600 millisecond as well after the onset of cognitive conflict is another key aspect that affect cognitive conflict, if that answer your question.
Yeah, I got answer. Thank you.
Well, I'm very close to finish as well, so I can take more question. Literally a couple of more slides. So why I'm showing this example, essentially, I just want to broaden the view that this cognitive conflict literally exists, literally every interaction we do every single day with everything. So cognitive conflict happen all the time. And that signal, that information can be used to adapt their surrounding. So either it's a navigation or either it's a robot interaction or car driving and so on, even reading a book or having entertainment, watching a television, for instance. This is all entertainment sort of direction, but also possible to use the same information to diagnose people. So, which which I don't do, but just for example, a person who doesn't show very strong cognitive conflict signature could be representation of ADHD, attention deficit hyper disorder, for example. It also represent, so if there's a disruption in cognitive conflict in someone's brain, that might be indication of certain brain disorder. That's what I'm trying to say here, which is a very interesting direction to explore. And I think there have been few works you can see outside. That's where people are trying to do. And one of the work where we are trying to do with the navigation. Now, why navigation might be interesting here? So this is augmented reality where you don't need a closed space, but whatever you see as a reality is augmented. Now, this study is very important because navigation have strong relation with Alzheimer, and a person with a poor navigation ability have higher chance of having memory issue in the old age. So we want to understand first, is there a way to understand how navigation work? And can we encourage user to become more better in navigation? Because Google Map and so on are kind of not so great to help in navigation ability of individual user. And because it's related to dementia and Alzheimer, so it's good to train yourself in certain way that it improve your navigation ability. So we designed this experiment. Now this experiment required, so you can see this little screen here on the top, which is an augmented reality based interface. Now this arrow is a representation of very similar to Google Map, but if I can play it again. So this arrow is a Google Map representation. There's a little map as well, and this is still Google Map kind of thing. Now here is user is looking at Opera House and UTS building, sort of this very short video. It's like if I told you follow the east because sun is in the east, or follow the North Star and just keep going that direction. You somehow still navigate by yourself, taking left and right turn and learn around surrounding while reaching the goal. Now, how neuroadaptation is happening here, because everyone have different strategy, it's possible to adapt that information depend on the user requirement. And that's where we did a little bit navigation and neuroadaptation here. So these are the example I hope is helpful. And this pretty much very end of what I want to share. And obviously this is not possible with several student and colleagues and of course funding agencies, which I was a part of, fortunately. So thank you everyone, and happy to take as many as question you want.
Thank you. Thank you very much, Dr. Avinash. Lot many take-home messages as well as lot many queries we have. So I'll request audience to please start putting your queries so that Dr. Avinash will be able to answer.
Well, I can read the very first question from Dr. Jaspal. Is it dynamic adaptive BCI? Yes. It's a real time, if you mean by dynamic that, but it's not so dynamic. You also have to understand what to adapt. So if you just feed every information into the model, it just doesn't know what to adapt. So for example, the very first example of virtual reality, maybe I can stop sharing my screen first. If I take very first example of virtual reality, so we adapted how to interact with the little cube, the timing of the little cube, and the timing help us to adapt that little information and user become more. So essentially we have to know if user feeling less cognitive conflict or more, I mean the range. So when user feeling less cognitive conflict means user feeling more compliant or more consistent with the cognitive conflict setting, whatever presented to them. And so yes, dynamic but strategic, if I say so.
Um,
Hello, sir.
Yes.
Sir, while you were discussing about the gripping machine, I want to uh, know the over gripping and under gripping difference again, sir.
So
I missed that.
that's all right. Overgrip essentially is just holding so tight. That's called overgripping. So if I give you a tomato and you hold so tight that tomato just burst, that's called overgrip. And undergrip is I give you something to hold, but instead of holding, you just fall down and slip from your hand. That's what you call undergrip, if it makes sense.
Yes, sir.
And this could be a range, right? So how to overgrip and undergrip, this could be a range, and we try to adapt this by brain signal. So that's not motor imagery, we're just using cognitive conflict because it can be just go very real time, pretty much every 200, 100 millisecond. And we can just feed that into this gripper to let it learn how to grip, essentially.
Thank you, sir.
No problem.
Other questions, please. Yeah, I have one question, Dr. Avinash, related to some other work of ours, where we are trying to capture the attention and the focus related cognitive functions of a user doing some while doing some of the maybe the basic thing called EEG data acquisition. So when we are doing the data acquisition, a person who is wearing the EEG headset after taking a lots of experiments, so definitely the person gets fatigued, kind of the load he is wearing. The question is related to two aspects. One thing is about when the person is getting fatigued. Second thing, and the then person is performing any attention based task while doing the data acquisition. In case we are getting excess of delta wave, means the very higher peak in delta wave. So do you have any, means this is very prominent case which generally we are getting in most of the cases. Most of the cases means not only in attention oriented task, apart from that when we are doing some stress task as well as some stoop test tasks. So generally we are getting that very big prominent delta wave in all those data acquisition. So do you have any observations or feedback on this thing, or means any solution to get this problem solved?
That's interesting. Yeah. But if I ask you following question before I answer, even you getting strong delta wave, does it affect your data? Because you can filter it out.
The question is that if we are filtering that out, so there may be a loss of information as well. It wouldn't be like that we are missing some important information which is deviating our task, because we want to identify whether the person is in stress or non-stress situation, whether the person is in receptive mode or not in mode, or the person is putting attention or falling asleep. So the classification is based on that itself. So if delta wave is coming very higher, so in that case we are not able to identify whether the really person is falling asleep, or whether he is not putting attention, or the focus is losing, or means on what basis, on what ground we should detect that, detect means the discard that delta wave.
Well, if I were you, I will look for, I believe you also do more independent component analysis. I'm not sure you definitely perform. And looking at more closely, if it's really originated from the brain, because I feel like it could be a noise itself
uh,
alone.
uh,
Hopefully
mhm.
it's a brain signal. If it's a brain signal, yes, it's important. If it's not, so without even filtering it out, you can just remove that certain component which might be the contributing that strong delta wave. And actually, lower frequency are very prone to have noisy signal, and something around 10 hertz, something around 50 or 60 hertz, depend on the AC power. So these three places, you always see the noise. And if you're seeing more and less, this could be the result of maybe user stop. I mean, mind wandering is another example where delta is actually happen a lot, because
Yes,
you
yes.
mentioned attention and fatigue. So could be just relation to the brain signal. I mean, it's an actual prominent signal, and maybe that's what it causing it. That's what
Yeah,
I can think. So I
yeah,
mean,
that's good. Mhm. Yeah, please go ahead.
I'm just saying, so maybe it's a good thing, it's not a bad thing. But again, one way to avoid that, I think, to make sure the trial selected by you is really a trial when user is actively performing it. But again, the task itself is an attention task, then yeah, that could be a tricky element as well. So make sure maybe participant actually respond to certain things when they're performing the task to make sure they are on the task. It happened very easily that you participant just going here, there, and mind wandering and so on.
So you never came across such kind of
I did, I
repetitive
did,
delta.
I did. And so what we do, so there's a, I mean, it's a very popular technique. Well, so many people use. It's not technique, but it's just a way of handling the data. So first you filter the data with that particular area and just go through the data. So let's say you go and filter the data from 1 hertz itself to, I don't know, 45 hertz, and do some analysis on that data, especially the component analysis on that data, and that take the component analysis of the data and bring back the data to original data, which is not filtered from 1 to 45. Instead of it may be filtered from 0.1 to 45 hertz, and copy that information there and just analyze the data based on component. It will minimize the issue with the delta. That's what I can recommend, and it really helps a lot. So in a way, you're analyzing with delta without losing any information, but at the same time, if it's a noise, it might already get rid of because of component analysis. And that's very helpful.
Yeah, got it. Another question of mine is about you. Do you have some hint or kind of what procedure methodology we should imply for getting proper attention level? If my task, my objective is to find the attentive level of the user or the person, so what would you prefer? What would you suggest for us to Means like frontal lobe is one of the thing, theta beta ratio is another thing. So what else you would tips you should give to us so that attention task would be more prominent?
Yeah, attention is always, I feel, same time easy and complicated. Like you said, those two are very prominent measure. I mean, alpha power alone can measure a lot of things, right? You just look at the inverse of alpha power spectrum and it just give you different level of attention changes very quickly. But attention depend on what kind of attention we're talking about. Visual attention.
Yeah, miss, while performing some of the studies related to neurofeedback, because we wanted to do some of the experiment where we, by neurofeedback, we wanted to make user make means elicitation of attention. They're performing some kind of gaming experiment. So this is what we are trying, and somehow that very first thing is about the delta wave, which is blocking our ways first, and then identifying the crux of the things, how we can evaluate whether the person is literally paying attention or not.
Right. I think that the frontal and parietal lobe, the ratio of different wave, I'm not exactly sure which one is was that. I read few papers. They are very robust, I found. If you're already using that, that's great, but not just frontal. So look for frontal and parietal. And the ratio of these two could be very strong measurement of attention in real time. And of course, it's based on power. There's a power analysis. So if it's a real time, bit problematic sometimes. But the relative power is very helpful in that case as well, for the gaming purpose, if you say so, if it makes sense. I think that's the one way. And like I said, attention is quite broad field. I think it's lots of things happening. So there's a one experiment we are performing where we're looking at overt and covert attention, for instance, all related to visual attention. Covert attention is essentially looking from the corner of your eyes, peripheral vision, base attention, and one with the primary attention. And you can play with different media. So for example, one tricky way to measure attention could be SSVP. So
Yeah.
if you can pick up the SSVP, you can say user is paying attention to that specific scenario in front of. So SSVP could be placed as a beacon to keep user in check in and through the real-time processing. So sometime you have SSVP suddenly happening, and if user is playing the game or paying attention, you know user is paying there, because attention SSVP only will occur when there's a, or RSVP is another potential way, very similar to SSVP. It's a trick, but it works very strongly. Are you muted?
Yeah. So sorry to take further more time, because it led to one more question to me, because
Yeah.
somehow we have got bit of the expertise, not expertise means experience working with SSBP. So how means okay, we are having some of the frequencies flickering on our screen, and we are able to capture the screen by the methodology of EEG processing, what we are doing. So if the wave frequency, brain frequency is matching with the SSBP frequency, so you want me to understand that the person is putting attention. So it
So
would
I'm
be kind of a
saying
regressive attention, and the classification of attention is some threshold should be there by which we would be like 8 hertz. It is flickering on screen, and my brain waves are coming. That is also coming on the 8 hertz frequency.
that's
So
right.
somehow it would be giving kind of okay, the person is giving attention, but there should
That's
be
right.
some threshold to check whether the attention is okay or not. So what should be the threshold?
Well, yeah, I think I understand. You're looking at the amplitude, for instance, here, right? And maybe it reduce. I think as long as you can detect SSVP peak, and it's a peak in certain range, it's already a good chance that user is paying attention. Now, I can't say it's very strong attention or not. It's not possible to say by just looking at that. But definitely, if it's a detectable peak among all the frequency, that means the user is paying a lot of attention versus no attention. So as long as it's a peak, the maximum peak among your spectrum, I think that's itself is a simple measure. Is there any amplitude? I don't think there's amplitude. Maybe if it's below half a hertz, going below that, maybe it's not quite clear SSVP at all. But I think having this random flickering in the middle of the task that user doesn't even prepare and ready for, It's a very interesting and tricky way to make sure
So
user is
that
in
that
check.
would lead to P300 again then. Miss.
P300 could be as well, yeah.
Hmm.
Actually, it will not be, it might be a combination of P300, but SFCP for sure. And I find SFCP compared to P300 is very nice and simple measure that you can simply detect from occipital lobe and just look at the frequency domain and just see, oh, there's a peak, right? The user is in the doing the things. It could be a mix of frequency, for example, 8 hertz or 15 hertz and so and so on. So it's also you make sure the peak is not just there because by chance, but you are getting the peak what you have shown. So you check your peak is there for 5 seconds and user is also have that peak in that duration. That means it's all good. I think same can apply for cognitive conflict kind of thing as well, but um, based on the sound. So you can keep checking the user without telling the user that you are checking. So that could be a tricky and interesting, actually more robust way than attention itself. I think there's one question about MATLAB or Python. Well, I use both, to be honest. MATLAB, of course, is very nice when you're analyzing the data, but when you take the analysis and try to build this real-time system, then we generally move on Python. So really, whatever we need, we just use both and as we go. And the most of the time, EEG Lab, which is very popular tool, I think some of you might be using, is the start where we analyze the data. And in the Python world, there's a MNE, which is another very popular tool, can be used to analyze the data. No problem. Which channel can be used for P300? You go in the frontal lobe. Generally, well, sorry, not frontal lobe, parietal lobe. Like a PZ is a very good location, or surrounding channel of PZ can give you P300. So anything around the visual cortex can give you P300 measure, and it slightly change, not always in the center. But PZ or P3, P4, they can all give you a P300, very nice one. Connecting well, you can have more measure, more useful thing. Yes, depend on what you want to do with that. Connecting measure is very nice thing to do. It can give you a lot of information, how the information flow might be happening. That can give you a lot of information how to control that thing. But if you're designing an interface like a BCI, maybe connectivity analysis in real time is a bit complicated. So one thing I want to highlight, when people say BCI, there's a lot of people say BCI, which is simply a running a data in the machine. It's not necessarily qualify as a BCI. Uh, I'm talking about the BCI, which is real time. You put the user in there and you real time detecting everything and doing things. Then connectivity measure, it might be a bit problem, which means it's very, very slow. You need enough data to go with that. So it's a good feature for offline analysis, might not be very good feature for online, but I believe there are people who may be trying this approach. So maybe it's a problem how to find the best real-time connectivity measure.
Yeah, do we have any further question, please, from audience? Seems that we all have got that cognitive load of understanding so many things. So good. I think this is a very interesting and very insightful session, and we have lot many take-home messages. We learn lot many new things, though we are working in this domain, and but still, the more we learn, the more we know that how much to learn more. So this is same here for all of us, and it is really a very, we enjoyed the session very much. Thank you, Dr. Avinash, for your time and your knowledge sharing with us. We really appreciate. And I thank you for all the audience for being present. And I hope this session has been useful for all of us. So thank you, all of you.
Thank you, Dr. Priyanka. And anyone, feel free to reach out if you think I can help you with something. And I'm very excited that lots of thing happening in CDEC. Actually, I was not aware there's a BCI work happening in CDEC. So that's a great initiative, Dr. Priyanka and your team, I assume.
We'll connect further sometimes so that we can have more internal discussion and detailed discussion on the topic. So we'll catch you back again, sir.
Thank you, Dr. Priyanka. Bye, everyone.
Thank you.
Thank you, sir.